Hi, my name is Peyton and I am in the Mechanical Engineering Introductory Course 150. Today we're going to be talking about the Pasco smart carts. We used these smart carts to test 3 different physics laws. So we tested Newton's third law, we tested Hooke's law, and we tested friction. With these carts, we can test all of these different things because it has several different sensors, including acceleration, force, and it has a velocity sensor, including its gyroscope type sensing elements, which can sense the direction in which the cart is being moved, which I think is really cool. The force measuring up to 100 newtons, acceleration to 16 grams, and position measuring by 0.2 millimeters, which is pretty cool considering that it's a Bluetooth device, which can also be connected through USB. The software that we use that's compatible with the carts is called Capstone. We used it on a laptop. We did not seem to run into any software issues. I believe because we've used the software before using the Pasco bridges and the force sensors with those, but it's a very easy to use system. So the first law that we tested was Hooke's law, and Hooke's law states the force F needed to extend or compress a spring by some distance, which is represented as delta X, is proportional to that distance through the spring constant K, where K is the constant characteristic of a spring's stiffness. So when we are pulling something, we're putting tension on something, it'll measure the distance in which that is being pulled. So all of the procedures for all of these experiments are in our reports. So I'm just going to quickly go through the results and whatnot. So we found the K constant using F, which is force, is equal to delta X times K. So we rearranged this and we did delta X, force divided by delta X to find our K constant, or we could find it through the slope of the line that we graphed using the Capstone software. It was very simple. We pulled the cart back, the software measured the distance in which we were pulling, the force that it used, and we were able to find the spring's displacement, or the stiffness of the spring, using the slope of the line that was created. So we used 2 different springs. We used a longer spring and a shorter spring, and we measured both of the K constants for those, and then we connected the 2 springs together and measured the K constant for that. We were able to find the theoretical constant using the equivalent spring, or the series spring equivalent equation, which is K equals K1 times K2 over K1 plus K2. The theoretical being 3.616. Our results, our actual being 3.49, which is very, very close to the theoretical, giving us a 3.61% error. So that was the displacement of both of the springs connected. The individual spring K constants were in our reports. So moving on, we go into friction. There's several different kinds of friction. This experiment mainly focused on kinetic and static friction, and we could find both of these using the same equation but with a different format. So using the force and position sensors, we pulled our cart along with a friction block or a weighted friction block. We used different masses. I believe we used 4 of the 0.25 kilogram blocks on one trial run, and then we used 8 of the 0.25 kilogram masses on the second one. The position and force sensors seemed to work without issue, giving us believable results. It turned out that the static friction was slightly greater than that of the kinetic friction, which I believe to be true. I think these carts are really great because the wheels don't have all that much friction. If any, it's a very small amount of friction, so the wheels don't affect the results as much, which is nice. So we get a pretty accurate reading. In the future, if we were to do this experiment again, I believe doing this on different surfaces rather than just the Pasco track would be really interesting to see how the surfaces would affect the friction block and the weights. And then for our final experiment, we tested Newton's third law, which is for every action there is an equal and opposite reaction, which is represented by F of A equals negative F of B. So for this, we used 2 different graphs for both red and blue push, one acceleration and one for force. In our experiment, our blue cart is 3 times the mass of our red cart because we put 2 of the 0.25 kilogram masses on our cart, and each cart weighs about 0.25 kilograms. So that being said, it's 3 times the mass of our red cart. So when looking with our red push, by red push I mean we pushed our red cart against our blue cart, moving the blue cart along the track with the force of the red cart. The forces were about the same. We did that for both of the carts. We did the red push and then the blue push. The forces did not change, but the acceleration needed for the red cart was 3 times more than that of the blue cart, which is understandable because the blue cart was 3 times heavier than that of the red. So force stayed the same, acceleration was 3 times the acceleration of the blue. This can be used in a multitude of scenarios. The one that we used was 2 different cars. So if you have a 100 kilogram mass car and a 300 kilogram mass car in a head-on collision, the 100 kilogram mass car going 30 miles per hour, which is the 3 times acceleration, versus the 300 kilogram car going 10 miles per hour, the force of the impacts would be the same because this power is equal to this power. However, if both of the cars were going 30 miles per hour, the impact on the red car would be 3 times greater because it's 3 times the power that is being used. Overall, I believe that these carts are really great for experimenting. We didn't have any problems with any of the software, and yeah, so thank you.